Okay, in this video, we're going to focus on how to sketch our graphs or curve sketching. Whenever you're going to try and sketch a graph from an equation, there's some key components or key points, identifying things that are elements that will help us as we graph it. One of the first things you want to do is get familiar with the parent functions. This will help you identify the domain that exists there, and then you can apply any transformations to modify that domain. One of the key points that will help with is finding our vertical asymptotes and our holes as we identify places in the domain that cannot be used or doesn't exist. Vertical asymptotes in particular occur when we have rational functions in which we have a factor that is found below in the denominator that cannot be eliminated by a corresponding factor in the numerator. And so this creates a vertical asymptote. A hole is found when we have a factor in the denominator that can also be found in the numerator. So in this case, we had x plus a and x plus a in the numerator and denominator. It would still not exist, but it would be a hole instead of an asymptote. So these two are key points to find, especially when we're getting ready to graph this. X and Y intercepts, things that we've been finding out since algebra. To find the x-intercepts, we set our y equal to 0. Y-intercepts, we set our x equal to 0. Both of these should be written in an XY or ordered pair form. This helps especially to remember to graph those points or graph the holes as you begin to graph. One of the things I neglected to point out is that you would also put your holes in an XY or an ordered pair form. The end behavior would be the next thing. Now, the end behavior is again determined a lot by the parent function. Just some examples here. If we have an even polynomial like x squared, and even is x squared, x to the fourth, x to the sixth. If it's positive, then our end behavior is going to be going up like a parabola. If it's negative, I'm going to go ahead and do this in a different color. If it's like a negative a, so it's like a negative x squared, then our end behavior is going to be going down as we go towards infinity. Same thing occurs when it is a odd polynomial, like x to the first power is an odd factor. X to the third, fifth, that kind of thing is all that way as well. When we have that, the odd polynomials are end behavior goes from the negative, where x is negative, y is negative, up to the positive in kind of an uphill type slope. If we have a negative odd x, first term, like a x to the x cubed, where a value is negative, then our slope is going downhill from the negative x, positive y, down to the positive x, negative y. Some other things to keep in mind as far as in behavior would be if you have an exponent or an exponential or a logarithmic function, how the negative side on a exponent function goes towards 0, or in a logarithmic function, how the end behavior as it approaches 0 goes to negative infinity. There's a variety of end behavior that you should be aware of, again, based on the parent functions. Now, even in odd asymptotes, anytime we have an asymptote as we learned in one of the previous lessons, the number of times or the redundancies of that that vertical asymptote, or that point, will determine whether it's an even or an odd, and how the end behavior works there. So if we had our x plus a, and this was squared, which would be an even, wherever our a is, it's going to create. So if our a was down here and this was our asymptote, then the end behavior as it approaches that asymptote is going to be on the same side as you approach it, either from the left or from the right. If it is an odd redundancy, so if our x plus a was like cubed in this case, or one time or 3 times or 5 times, then our end behavior here is going to go on opposite sides. And so this would be something like this as an example. So that covers most of the primary identifiers that we're looking for, the special or key points as we go through the graphing. Let's take a look at some of these to begin with here. We've got 3 problems, and we'll just kind of focus on figuring out how the best way to come up with the key points here. So first thing we're going to look at is our domain. Now the domain is identified primarily, at least exceptions with rational functions, by what becomes 0 in the denominator. So in this case, we could do a quick factor of this. This is going to be x and x minus 2, and we would factor that out. Now, in this case, there's no common factors in the numerator and denominator, but this factor here shows us that we have positions at 0 and 2 that cannot exist in our domain. This is either going to be asymptotes or holes. In this case, it is going to be asymptotes. And so we've got a vertical asymptote at x equals 0 and at x equals 2. We know they're vertical asymptotes because there is no factoring in the numerator and in the denominator. Now, the final thing, our end behavior, we can identify some of the end behavior by taking a look at our first term in both the numerator and denominator. And so in this case, our numerator has an x as a first term, denominator has an x squared. This can be reduced to 1 over x. Now, as we go towards infinity, this is going to show us that the larger the number in the denominator is going to get closer and closer to 0. So as x goes to positive or negative infinity, our y is going to go to 0. So it means that we actually have a horizontal asymptote at y equals 0. Y equals 0. Okay, so this is our end behavior in this case here. If we go to the next one, number 2, again, it's a little bit different, but it's still a rational function. We're going to look at our domain. We're going to find the places where it cannot equal or cannot be used. And in this case, it's the denominator. So x cannot equal our negative 3. Okay. We also have a vertical asymptote at negative 3 because there is no common factor between the numerator and denominator. So we can look at this and identify our vertical asymptote at x equals negative 3. Now, one of the things I forgot to do on this previous one, if we identified each of these vertical asymptotes, we might as well identify whether they're odd or even. In this case, x, that's even, or that's an odd. X to the first power, that's odd. This x minus 2 is also to the first power. So both of these are odd. Okay, if we take a look at our number 2, this has got an even power right here because it's squared, so this is going to be an even asymptote. Okay, the next thing is to identify our end behavior. This is going to be done by taking the first term in both the numerator and denominator. Numerator is easy. This is going to be 2x cubed. It gives it to us. The denominator, we need to make sure that we take that first term and we square it. So this would be x squared, because that whole factor is squared. So this becomes 2x cubed over x squared, which can reduce to 2x over 1, or just 2x. Now 2x, this y equals 2x. That's a linear function, and it's a positive linear function to power of 1. That means our end behavior is going to go up on the positive side and down on the negative side. Okay. Our next one is the number 3. We've got another rational function. This rational function has gone ahead and factored it out. We take a look at our domain and identify what we can't have in our domain. So in this case, our x cannot equal negative and positive, negative 2 and positive 2. We're going to go ahead and reduce this. That's what this h red of x is. We're going to reduce this. We do that by clearing the factors out between them. Now, x minus 2 is in the numerator and denominator, which means we have a reduced function of x plus 4 over x plus 2. Okay, now let's go back to the places where it can't exist in the domain. The first is a negative 2. Now the negative 2 is going to be an vertical asymptote. And this is going to be an odd vertical asymptote. This is because we have this factor left in the bottom here that does not have a matching factor in the numerator. We also have a hole. Now this hole is found at 2, and we need to plug that value in to our reduced function here, our reduced expression. So 2 plus 4 is 6, so it'd be 6. And 2 plus 2 is 4, so our point would be at 6 over 4. We can reduce that if we want to, which would be 3 over 2. Okay, so that's where our hole is. Finally, our end behavior. Now, we again would take the highest term, which in this case is an x squared over an x squared. So x squared over x squared, well, that reduces to 1. So our end behavior is we've got horizontal asymptotes at y equals 1. So horizontal asymptotes. Okay, we're going to go ahead and continue on and take. Actually, I'm going to create a part 2, and in part 2, we're going to continue on with the other examples for graphing and actually do the graphing itself.